and you own a company. Now, this company of yours deals in products and services, and you obviously want to improve your company by dealing with the problems or inefficiencies which are present. But to do so, you will first need to identify the problem, and for that, you need feedback or reviews of the company. Back then, there were few ways to give feedback, and most of them were unattractive to consumers. Writing a letter to the company, which will probably not even be taken seriously and might not even reach the company at the first place, few people were willing to go through such efforts. And so, companies had very little to no feedback. Fast forward 20 years, and we are in the digital age. Due to the internet, finding and dropping reviews related to products is very easy, and now you have a constant stream of feedback data. Does this solve your problem, which was to deal with the problems and inefficiencies in your company? Are you now able to improve your company by identifying the weak points? The answer is no. In order for your weak areas to be identified would require a group of people to go through all the customer reviews one by one, and the research would have to be split. Since your review data would be huge, it would have to be split amongst many employees, and there will be like 1,000 odd reviews on Amazon alone, then Flipkart, Instagram, Facebook, Twitter all combined, and we are talking about a lot of reviews. Let's take 5,000 as an estimate. So this team of employees would manually have to read every article or review and combine the information to identify patterns or common words in the complaints or reviews to know where the company needs to improve. Using sentiment analysis, you can track the customer sentiment versus time. You can review. You can do customer review segmentation, right? You can extract your areas of improvement as we discussed. You can predict stock prices based on the wordings of the tweets related to those stocks, right, or the news related to that stock. And you can, even based on the wordings and profile of the customer, how many products he has bought, whether the customer regularly posts reviews, you can analyze which complaints have to be prioritized. Now these are only a few use cases of sentiment analysis, but there are many more. Today in this project, we will be covering how to create a sentiment analysis model using machine learning that can analyze Twitter data and extract the sentiments by itself. For this to happen, the machine would have to first be given a vast amount of data to learn how to correctly analyze the sentiments behind the words. This data can be collected using either a data set available on Kaggle or using a web scraping. Web scraping is simply the process where you train a Python script or Python code to go through all the data on the web related to one subject and get all that data to your computer. After getting your review data, the data is now will be in text form, but a machine learning model cannot understand words. It can only understand numbers, and so we must convert our word data into numerical data. After this, we can train our model on the data by giving it the tweets and whether they are real, fake, or neutral. And after verifying the two against one another, the model will be able to see what words are common in positive tweets versus negative tweets, and it will be able to predict whether the tweet is positive, negative, or neutral in nature. Now, there are some problems or challenges that are commonly faced while making a sentiment analysis model. First of all, it takes too much processing time. Since we are talking about getting data from 4 to 5 data streams, Amazon, Google, Instagram, Twitter, Facebook, all the data when combined will be too much and will take a long time for the model to process. In our case, we have 1.6 million tweets that we will be analyzing. So we too will be facing the same issue. Another problem is that the model doesn't understand the actual meaning behind the words. If we just randomly pick a number to represent a word, the model will not be able to understand what the word means. which will make it difficult for the model to understand whether the word is positive or negative. This would also cause the model to be unable to understand which words have higher impact. Love is a more positive word than like, so it should have a greater impact on the tweet's overall sentiment score. Another issue, so a very popular method to solving the text data problem which machine learning models face is to use one hot encoding. All one hot encoding does is it creates a separate column for every unique word in a statement, and then based on whether it appears or not, puts 1 under it or 0. So for example, there is a statement, um, Elon Musk buys Twitter. So as the words Elon Musk buys and Twitter, all these 4 words appeared, they will all have 1 in their columns. But Facebook will have 0 since it was not mentioned in the article. However, this makes the model, first of all, it makes the model too large, and in the case of 1.6 million tweets, the data would become monstrously large because we will take every separate word from 1.6 million tweets. Also, it does not explain the actual meaning of the word to the model, just highlights whether it appeared in the tweet or not. Word2Vec solves both problems. It is able to capture the meaning behind the words without occupying much space and does not create too many columns or features for us to handle. Artificial neural networks or recurrent neural networks only have a short-term memory. So what happens is they go through a problem known as the vanishing gradient problem. The gradient is the the influence that every variable has on our predictions. And when our gradients become too small, every feature does not have almost any useful effect on our model, and so our model stops improving and just remains the same. So this problem mainly occurs in very large neural networks. LSTM solves that problem by keeping long-term memory stored separately so that every gradient still has a higher value and no variable loses its meaning. The way our model will work is highlighted here. I will explain the terms used here in detail in further slides. We will first load our data into the notebook using the simple read_csv command. Then we will use stemming and stop words and word2vec to pre-process our text data. After that, we will convert the data to 1 token per row format. We will then give each of our possible target variables or answers to the tweets a number to represent it, 0 for negative, 2 for neutral, and 4 for positive. Then we will feed our training data into the LSTM model and try to predict our test data before checking the accuracy. The way stop words work is that they leave only important keywords and cut out the rest of the words which don't add anything to the picture. Is, the, for, can, I, they all don't add anything new and are not required by our model since they don't have any sentiments or importance attached to them and are just occupying unnecessary space. Human beings need these words to make their sentences sound complete, but the machine learning model only needs the important words, the keywords, and these words are not helping it in any way except occupying space. The way stemming works is that it converts a word back to its stem. So it removes the part which adds tense. For example, for the stem of chang, change, there are multiple branches. There is ing, changing, ed, changed, and e, change. But what it does is it removes those branches, reduces it to its stem chang. Now the result of stemming is not always readable by humans, but machine can understand the output. Tokenization is simply when we split a sentence into 1 word per row format so that the model can better analyze the sentiments behind each word. Word2vec is the central uh, technology which we will use. So word2vec is used to convey the actual meaning of a word to a machine learning model. So the way we understand a word, we know the meaning. If you want the machine to understand the word in a similar way, you will have to use word2vec. And then using word2vec, the machine will also be able to understand exactly what a cat is. So what it does is, it takes a group of words and checks them against some conditions, asks some questions, and based on the answers, it generates a numerical output. Simply, if you had the word cat, it checks for a list of conditions or features, or it asks some questions, like is it a living being? Yes. So then it assigns a value between -1 and 1. So in this case, since the answer is mostly yes, dot 6. Feline? Yes, assigned dot 9. Human? Not exactly. So dot 1 will be assigned, since it does share some aspects with humans. Royalty? Definitely not. So minus dot 7. Now the result for the word cat will be something like dot 6, dot 9, dot 1 minus dot 7. But if every word has so many features, the computation will once again become quite large. So it compresses this 7-dimensional, 8-dimensional vector into a 2-dimensional vector, which has only 2 variables or 2 features, which will be derived by either multiplying or running some mathematical method on our other variables. So for example, cat and kitten, it will realize that the two words are very similar, since it can compare the features and find, okay, cat is living being, kitten is also living being, dot 6, dot 5 very similar, feline, dot 9, dot 8 very similar. So it's very similar, so the two words will be understood as being very similar. However, cat and house is not similar, and their features also will not match at all. So word2vec uses two central technologies. It is continuous bag of words and skipgram model. Now, continuous bag of words takes a randomly selected target word which it selects and tries to derive from it the context words or words surrounding it. Thus, it understands the relationship between them. Skipgram takes the target word and tries to derive the context, which allows the machine to understand which words appear more frequently with each other. Continuous bag of words understands which words are more similar in their alphabetical structure, like cat and cats are similar with the first three letters being the same, while skipgram understands which words are more similar conceptually. Label encoding simply converts word labels into numbers, and it is used for target variables. It assigns a number to each category in our variable, like the example shown here, and it gives a new number to each category. Why not use one hot encoding or word2vec here? Because our model does not need to understand what it is exactly what it is predicting, because that's not going to help the model. The model just needs to make the predictions based on what it has seen in the past, and we should be able to understand or understand or interpret what the predictions are. LSTM is a type of neural network that deals with vanishing gradients problem. Vanishing gradients problem happens when there is a very large neural network and the change of every variable on the output is so small that when it is multiplied by the learning rate, which is the rate at which the neural network will adjust itself to reduce error, the result is so small that it hardly makes any changes at all. So it stops learning, it stops improving, and it plateaus, the performance stays the same. So to deal with this problem, LSTM was created. LSTM uses a forget gate to maintain the gradients value to be higher, so that every variable has a substantial effect on the output. Confusion matrix is a visual representation of binary cross entropy. The way it So there are many ways to calculate error. There is mean absolute error, there is mean squared error. Mean absolute error simply takes an average of the total error. Error is calculated by your predicted value minus your actual value. The way binary cross entropy works is, it takes your predicted values and checks the values for each possible situation. For example, there are four possible situations if it's a binary prediction. Binary means there are only two options, yes and no. So one is that you predicted yes and it was actually yes, also known as true positives. Then it checks for true negatives. You predicted no and it was actually no. Then there is false positives. Your model predicted yes, but it wasn't. It was a no. And then there is false negatives, where your model predicts no, but it's actually yes. And then on the basis of this, you can see our model made 55 predictions as negatives, and out of them 50 were accurate. Now we will begin the programming part of the project. We will be using Python and Jupyter Notebook. Data acquisition or importing of necessary modules refers to where we call the important libraries which we will use. Libraries are simply where large pieces of code are given different names, so that you can just call that small name rather than calling that whole large piece of code. For example, if you don't know a person's name and you just know the qualities, so the way the model will work is it will take a list of all those you will have to give it all those qualities to for for example, if you don't know a person's name and you want to find out, so you will have to go and ask another person, hey, that guy with the brown hair, and the guy with the green eyes, who always wear glasses, who wears a jacket or those type of boots, for the person to be able to tell you what his name is. But if you know the name directly, which is stored in a library, or in our case some book, or in our mind, we can immediately say, I'm talking about that person, and you can take the name and he will immediately know who you're talking about. So same, we don't need to write the entire block of code, we can just call the name of the block of code and it will automatically come there. So import pandas as PD. This is for data manipulation, simply for us to handle the data. We want to increase the rows, columns, we want to multiply columns, we want to remove some rows. For all that you use pandas. We import numpy as NP. Numpy is used for all mathematical functions like addition, subtraction, mean, median, mode. Then we import matplotlib. Matplotlib is used for making charts, plotting, simply creating a chart of our data. Scikit-learn or sklearn consists of most of the important machine learning elements. So we are importing train test split, which will split our data in train and test sets. Confusion matrix. Classification report consists of all the statistics of our model, right? And we are also importing TF-IDF vectorizer. Next we are importing from Keras. So Keras is the deep learning library. So from this we are importing our tokenizer, sequential, because we are going to create a machine learning model, activation to define which activation function we'll be using. I will go into all of that. Dense, I will go into what that means. Dropout, all that. Factor declaration. So factor declaration is simply every model, every command has some parameters. Like if I say I want the average of 10 numbers, I'm saying 10 numbers, that is already a parameter. So even if I provided an 11th number, it's not going to average it out, because it was told to only give me the average of 10 numbers. So parameters is where we define on which way is our model going to work. So we are telling it you're going to run 32 epochs. Epochs as iteration, so you're going to go over the data 32 times, word to vec. Train size is 80%, right? Our column names are target, IDs, date, flag, user, and text. We are simply doing that, right? We are getting our user names by using regular expression. Also in Keras we are doing the same. We are saying our LSTM model will run 8 times on the training data, and we are going to take 1024 tweets at a time. That is going to be our batch size, and our sentiment thresholds are 0.4, 0.7. So anything below 0.4 is negative, anything above 0.7 is positive, anything in the middle is neutral. So data exploration is, now we're going to read the data and have a look at how it is. So we are simply reading the data from our CSV file, comma separated files, where our values are separated by commas, and we are printing its size to see how many records we have, which we already know, 1.6 million, but we are verifying, and we are getting the head or the top 5 records of our data. Next, we will decode our numerical values to words because we want to print a chart and we want to know. So 0 is negative, 2 is neutral, and 4 is positive. So we are decoding the sentiments and applying the labels. Using the lambda function, we will immediately apply it on the entire column rather than having to go one by one. And here we are creating a count plot. Simply we are saying how many negative, positive and neutral sentiment tweets are there in our total data set. So out of 1.6 million. Data pre-processing is where we are preparing the data for being given to the model. So first we are removing stop words. Here I am saying stop words dot words English, and that is because we are going to be removing English stop words. There are different languages. Each language has different set of stop words. Okay, we are also calling our English stemmer, and we are defining our pre-processing. So we are simply saying for every token which is not in the stop words, then stem it. So because we don't want to do unnecessary stemming, so only if the word is not in the stop words, then do stemming. We don't want to waste our time stemming words which are going to throw anyways. Now we are splitting our data in training and testing sets. Our train size was 80.8 or 80%, so we are saying 1 minus train size is the test size, which will be 0.2 or 20%. And then we are printing the length of training size and testing size to see how many records are in each. So approximately the data that we will the number of data points that we will have in our training data will be 1.3 million or 12 lakh 80,000, and the remaining 3 lakh 20,000 records will be in our testing data. We are continuing our data pre-processing. So here we are simply importing our word to vec model. We have already defined all the factors, so we are just calling the variable names. We are saying size equals w2v, which is short form for word to vec underscore size, or window, or min count. That is because we've already declared the numbers before. And then we are building our vocabulary, and after that we are testing. So we are saying, okay, which is the most similar word to love, and then based on this we can know if our model is ready to or not. And now we are calling the tokenizer, which will simply divide our data into one token per row, and we are saying what is the total number of words we have in our data. Now we are getting the labels and encoding them. Since I already explained, we are encoding the labels so that our machine learning model can make its predictions accurately. And we are using an embedding matrix, which is simply another part of word to vec. So what this does is it simply multiplies every vector. So every word has been converted by now into a number, a collection of numbers, which is called a vector. And now it is converting that entire vector into a value. Since the some vectors will be small, will have small values like 3, 7, 7, 3, while some vectors will have large values like 26, 52. Now we don't want that our larger value vectors have more influence, because just because they have a larger value does not mean that they should be given more importance. So we are using our weights so that all the words are treated equally. So our weights will just convert them all into values between 0 and 1. Now we are creating our model, our LSTM model. So first we are defining that our model is sequential. It's going to deal with the data one by one. And then we are adding our embedding layer, dropout.5. So dropout simply randomly drops some neurons. What happens is when neurons go through too much training, every neuron starts overtraining after a while. So to prevent overtraining, we drop half the neurons every time a new record comes. This keeps every neuron in balance. And we are defining that our LSTM is going to be dense. Simply every neuron is connected to the other, and we are using sigmoid activation function. What sigmoid does is it simply converts our predicted values into probabilities. So it will just give you the probability of the value being. Since we are saying it's activation sigmoid, what it will do is it will convert our values between from whatever big value we get 200, it will convert all those values between 0 and 1. Now we are compiling our model. As I said, we are using binary cross entropy loss function as our loss function. We are using Adam optimizer. Optimizer defines how you will change your weights or learning rates to achieve global minima. Global minima simply means lowest error. So to reach your most accurate version of the model, how much how are you going to adjust your values? Metrics is accuracy. We are simply saying that we want to increase accuracy, or to increase accuracy you need to minimize error. So it's the same thing. Now we are evaluating our model by getting the score, the accuracy, the loss, and here we are decoding the sentiment. So we are simply saying if score is less than sentiment threshold 0, which we already declared back then was dot 4, label it as negative. If it's more than 7, declare it as positive. If it is less than dot 5, return negative or else return positive, right? And anything between dot 4 and dot 7 would be neutral. Here we are defining our predictions. So we are simply asking our model to make predictions on the testing set, and then we are decoding our model's predictions, which are in numbers 0 to 4, into words: positive, neutral, and negative. So now our model will return the label simply, which is what is the answer, with the score, which is how accurate it is about its answer, the elapsed time, which is simply the amount of time it took for the model to make its prediction. And now we give it a sentence to predict the sentiment of. So we are asking it to predict the sentiment behind this sentence: I love the music. So which is obviously going to be high, but you can give it more confusing statements which make it harder for the model to be able to accurately predict what emotion is being conveyed. And now we are creating a confusion matrix. We are giving a figure size of 12 12. You can make it a larger plot, a smaller plot, but 12 by 12 is usually the standard. And we are saying for every unique value, okay. And we are taking our y-test one dimensionals, which is simply we are converting. So in summary, we had 3 problems in our model, and each have been dealt with. Too much processing time was solved by stop words and stemming, which removed literally half the unnecessary data, half of the data which was unnecessary. Models do not understand the meaning behind the words was solved by word2vec and embeddings, which clearly help the model explain what the words meant by using the features. And which words have higher impact was solved by LSTM and word2vec. So overall, there are still improvements which can be made. We haven't dealt with emojis, which appear a lot, not much on Twitter, but if you're analyzing text messages or WhatsApp chats, it's gonna appear a lot. But overall, this is one of the best solutions using the most recent and advanced learning algorithms like word2vec and LSTM.